Confirm that you got it. So today we're happy to welcome Noah Fleming, who will tell us about the latest news in total functional NP problems. So Noah, without further ado, please.
Yeah, so I'm going to be talking about this new result that shows that the class PPP of things reducible to the pigeonhole principle is not closed, Turing-closed in the black box setting. This is joint work with Stefan Grosser, Tony Patassi, and Robert Robert. It's for those of you who like proof complexity, this is secretly a proof complexity talk. So there should be interesting things in here for you. Okay, so in this talk, we're going to be focused on the following problem called pigeon. It's the pigeonhole problem. You're given a map from m+1 things to n things, like this, you know, yeah, it's a map. Typically, this will be encoded, like if you think about it in the white box setting, it'll be encoded as a circuit mapping. You know, encoding this thing, so in like a succinct representation. So we query the circuit, gives us the, you know, we query it maybe on some number I, and it tells us where the ith pigeon maps. So the white box setting, we think about this as being like an exponential size instance of the pigeonhole principle, so exponentially many pigeons, not so easy to solve in polynomial time. And the goal is to find a pair of pigeons that collide. Yep.
The circuit should be mapping to 0 to the log n as well.
Yes. Yes. Yeah. Yes. Hasty slide. This stuff is not going to be important. It's just kind of like what they do in the white box world. Yeah. I'm going to be focused on the black box world. It'll all be fine there. So think about this part. Don't think about my thing up there. Okay. Yeah. So you know we're given one of these maps. There's more pigeons than holes. Find 2 pigeons that go to the same hole. You know, this is pretty easy to do if you can look at all the pigeons, but if you have an exponential number of pigeons, how do you do this? So this problem is not, this is an example of a search problem, so we're looking for 2 pigeons that map to the same hole, and it's not obviously in P. Yeah, this collision here, it's a problem in total function NP. So this is a total function, meaning that for every input, any map from pigeons to holes, there is an output, there is a collision, and it's in NP. So if I give you the names of 2 pigeons which I claim map to some hole, you can check that they actually do map to the same hole efficiently. Okay, and yeah, TFNP. Okay, so the pigeon problem is like one of the main problems in TFNP. TFNP is the class of all total search problems that are have like efficiently verifiable solutions. TFNP is not believed to have complete problems, and therefore the study of TFNP focuses mainly on like defining subclasses which capture important problems. So here's the kind of map of TFNP subclasses. I'll talk about a couple of them. Yes, and we define subproblems as everything one reducible to a complete problem. So each of these subclasses do have complete problems, even though we don't think TFNP does. And each of these subproblems are mainly like, if you were to define a TFNP subclass, the way you would do it is you'd pick some problem that's like really important, and you look at everything reducible to it. So for example, the pigeon problem, like pigeonhole principle, this is like a very important problem in mathematics. We use pigeonhole principle all over the place. It's related to cryptography, things like that. We could define the class PPP, which is everything many-one reducible to pigeon. I'll define what I mean by a many-one reduction, but yeah, it's the same thing as in standard reductions in you know, standard complexity where we study decision problems. So PPP is one of the original 5 TFNP subclasses, and it's particularly important because it's closely related to cryptography. So it contains lots of problems in lattices and cryptography, such as finding collisions in hash functions, variants of discrete log, Blickfeld's theorem on lattices, and factoring if we assume the generalized Riemann hypothesis. Otherwise, factoring's randomized reducible to PPP. It's also very related to proof complexity, right? Like the pigeonhole principle is the canonical tautology that we study in proof complexity. So even though PPP and this pigeon problem is extremely natural, it seems to be much less robust than all other major TFNP subclasses. So every other TFNP subclass is closed under Turing reductions. But Buss and Johnson and also Daskalakis conjectured that PPP isn't closed under Turing reductions. So what's a Turing reduction? Well, we say that a class is closed under Turing reductions if anything that is reducible to that class by like many calls to that problem. So for example, here, maybe often we want to say R is reducible by many calls to pigeon. We get an input to R, we define one instance of pigeon, we solve it, define a second instance, solve it, so on and so forth, and eventually we can turn that back into a solution to R. So it's closed under Turing reductions if we have some reduction like this, we can turn it into a reduction that just uses one call to pigeon. So something like that. Okay. Yeah, so Turing reductions, many calls to the complete problem, many one reduction, one call to the complete problem. So yeah, all other major TFNP classes are closed under Turing reductions. And we want to show that this PPP class is not closed under Turing reductions. There's a small problem here that it's not hard to show that if you could prove any separation between any two TFNP classes, show that some problem in TFNP is not in some class, this immediately would separate P from NP. So we can't hope to do that. So what we're going to do instead is what everybody else has done, is study the black box setting. So study things relative to oracles. Yeah, and so Buss and Johnson, along with conjecture that PPP is not closed under Turing reductions, asked for evidence that this conjecture is correct by proving a black box separation between PPP and its Turing closure. Okay. And that's the main result of our work here. So we managed to show that PPP is different than things that are than like the Turing closure of PPP. Okay. So any questions at this point? The result pretty clear. Yeah. So in the rest of this talk, I'll tell you how we do this, and it has some neat connections to proof complexity. Okay. So what is black box TFNP? So in this setting, the input is given by an oracle, and we can query.
There's a question from the audience.
Oh yeah.
So is there a notion of adaptivity here? Can
Yes.
we do adaptive or non-adaptive queries?
Yeah. So I'll get to that in a minute, but our separation holds even in the non-adaptive setting. So in the adaptive setting, it's like this picture here. So this is adaptive, right? So I define one instance of the pigeonhole principle, solve it, use the solution to that to get a second instance. A non-adaptive one would be I'd have to define all my instances of pigeon in parallel. They can't depend on each other. And then I get a solution to each of them, combine those to get a solution to the final problem. So the non-adaptive setting is weaker, and we actually separate pigeon, like PPP, from its non-adaptive closure as well. Yeah. Okay. So yeah, in the black box setting, so we're given, the input is going to be given by an oracle. You can query the oracle to find out, so you ask it the index of the pigeon, where does pigeon I fly, and it tells you the hole where pigeon I flies to. And this is different from the standard white box setting because we're no longer allowed to see how the input is defined, this circuit that I mentioned briefly at the start. Yeah, so this black box setting doesn't seem, well, hopefully is pretty, yeah, like a good model for the white box setting. In particular, all known containments in TFNP hold also in the black box setting. So we hope that this is a good model for how things are actually behaving. Yeah, and should also define what a many-one reduction here is in the black box setting. So we have a problem here. So this is like the input set, this is the output set I'm writing as a relation. This total search problem here reduces to an instance of the pigeon problem. So we can basically use standard like NP reductions or polytime reductions, but since we're working with search problems, right, we are not outputting just like 0, 1. We're outputting some solution, and we need to map that solution back to a solution to P here. So we're going to need like, it's going to be our standard polytime reduction, but we're going to add on like a little piece to it. Okay, so a many-one reduction setting. Since we're in the black box world, we're going to be using decision tree reductions. So we have a set of decision trees, T1 up to Tn, where Ti defines where the ith pigeon maps. So we query this decision. So we're given an input X to the pigeon problem. We query the decision tree, Ti, on input X, and it tells us where pigeon I maps. So yeah, we put X to this problem P. The trees give us an instance of pigeon. We can then solve this instance of pigeon to get a solution, a pair of pigeons that map to the same hole. And then we need a way to turn it back to a solution to P. And this is just another set of decision trees, one for each solution. So here we would have one for Pij, since Ij is a solution. And it maps it back. Yeah. So, yeah, decision tree reduction is pretty simple. Set of decision trees mapping the input from P to the input to pigeon, and a set of decision trees mapping solutions to pigeon back to solutions to P. And we're going to say this reduction is efficient if these decision trees are polylog depth, and n is, oh, sorry, this is wrong. Okay, so this should be, this log shouldn't be here, the log should be in front of n. Otherwise, this doesn't make sense. You can't have n being polylog. So this n should be, yeah.
So a naive question, can you comment on the notion of reduction? Because a priori, like you would just say one circuit that takes takes your X input to a pigeon, and then another circuit that just translates the solution back, but somehow it's the same. You want you want somehow the computational model for the reduction to be very, very weak, so that it sort of doesn't compete with the circuit in the same way where like if we're doing, I don't know, if we're looking at space, then we might want to have only logarithmic space in our reduction function or something. Should I think of the decision trees while you're insisting on those, that you want your reduction to be weak?
Yeah, yeah, exactly. It's going to be polylog depth because we're scaling everything down. We usually think of pigeon as being like an exponential size instance of the pigeonhole principle. There's 2 to the n many pigeons. Now I'm scaling everything down to be n many pigeons. Of course, this is solvable in P. So I'm also going to scale down the amount of computational power that I'm allowed to be polylog being efficient. Ignore this expression. That expression's wrong. I'll say what it should be in a minute. And then, yeah, this is like the non-uniform version of a reduction. You could define a uniform version where you just have, just a single map. But basically what it's saying is that, yeah, each pigeon is dependent on a small number of bits to of the input to P.
Shouldn't there be n plus 1?
Yes, probably. Yes, yeah. There might, yes, this should be n+1 because there's n+1 pigeons. Yeah, and so what should this expression actually be? So I want that, I want the depth of the decision tree, so ignore the log's wrong. It should be max depth of this trees among all these trees here. I want them to be small, so polylog. And I want n, the number of the decision trees, to be also roughly the size of the input here. So this should actually be log t plus max depth, capital T, is equal to polylog t. So basically I want, yeah, I could, actually.
Yeah, you're saying, okay, yes. I mean, because you could also, like, you don't want to blow up. Like, n should scale roughly like size of t somehow. Is that what you're...
Yeah, and basically n here is, I want n to be, yeah, roughly t, maybe a polynomial blow up in t, but I don't, polynomial here is like polylog, so polylog blow up in t, but I don't want it to grow too much, or else maybe I could use this to do some trickery, define an exponential size instance of pigeon, and then do some like trivia stuff. So I limit how many decision trees, like I limit the size of my instance, and I limit how much each decision tree can query. Okay.
So then in the end we get something like log n plus max log of the depth is polylog of t?
Yes.
That's what we get in the end?
Yes, it should be n. Okay. Yeah. Log n plus max is equal to polylog. Yeah.
Okay.
Yeah. So we're going to show that black box PPP is not Turing-closed. The first step to doing this, so the rest of this talk is just going to be outlining our proof, and then I will prove it formally in the second half. So the first step is to actually find a candidate problem. So a problem that's not in PPP, but is in the Turing closure of PPP. And the problem we're going to study is super simple. So it's this pigeon squared problem. You're given two instances of the pigeon problem, and you want to output a solution to both of them. So it looks like this. Here's two instances. These are two solutions, and you want to output like the concatenation of the two solutions. So the question is, can you solve this problem with a reduction to a single instance of the pigeon? That's the output. So yeah. So this is like essentially the weakest problem that we can think of that is not obviously in the Turing closure. I mean, not obviously in PPP, but is in the Turing closure of PPP. It's easy to see that this is in the Turing closure of PPP because you just solve the two problems in parallel, concatenate their solution, and output it. And in fact, as somebody asked about like non-adaptive versus adaptive closures, this is in the non-adaptive closure of PPP. So this is separating, so our result will actually separate the non-adaptive closure from PPP. Yeah, so we're going to prove that this pigeon squared problem is not in PPP. Yeah, I think it's kind of neat. You can't just like run the two instances in parallel. You can't make like you can't just stack them and try to solve them that way. You actually really have to use more power than just a single call to pigeonhole house. Okay, so here's the connections to proof complexity. So our proof technique is to use a lot of tools from proof complexity. There's a close relationship between black box TFNP and proof complexity. So I have this, I think it's like kind of exemplified by the following theorem that shows that for any TFNP subclass, there's a proof system P such that a search problem S is in this subclass if and only if P can prove the totality of S. So this means that for every TFNP subclass, I can define a proof system that's equivalent to this subclass. Here's our map of TFNP problems. Ignore this question mark for a minute, or TFNP subclasses. And here's the known correspondences we have. So we have, for each of these classes here, we have actually a natural proof system. By natural, I mean like one which we've actually studied basically before in the literature. Here, these U's mean unary, but it's just going to be how we're going to measure coefficients in these in these proof systems. By this translation, we do get a proof system for PPP, but I've labeled it by a question mark here because this proof system is kind of artificial. It's a Cook-Reckhow proof system in the formal sense, but it's not something you would ever like come up with if you weren't doing this translation. And I think a really nice question here is, can we come up with like a proof system whose reasoning power is captured exactly by the pigeonhole principle? This was one of our motivations for showing, for studying this question of whether PPP is closed under Turing reductions. We were hoping to use this in order to show that, in fact, PPP, the pigeon problem, doesn't have like a natural proof system that corresponds to it. It would have to correspond to something artificial. But I can say some more about that at the end.
Could you remind me who BFI are?
That's Bus, myself, and Russell and Pagliazzo.
By subclass here is like any set of different.
Yeah. Oh, yeah. So, so good. Yes. So, what do I mean by subclass? I mean any TFNP, any subclass, so subset of TFNP problems or of total search problems, which are reducible to one complete problem. So, yeah. So it's subclass just means something with a complete problem.
So I can take any problem in TFNP and then take the closure, and that's a subclass.
Yeah. Yes, thank you. That's an easier way to say it. So we're going to be particularly interested in this thing here. So there's also a question mark up here because there is a TFNP problem, TFNP subclass that corresponds to sum of squares, but it's not yet published. But yeah, so we're going to be interested in this particular like sub area of TFNP. Down here we have PPADS, which is contained in PPP. PPADS is characterized by Schiraldi-Adams by the following theorem, by a large number of authors. And up here above PPP is the class that corresponds to sum of squares. And this containment strict here, we know that Schiraldi-Adams can't prove the pigeonhole principle, so we have a separation between these two. And the idea of our proof is to generalize these Schiraldi-Adams lower bounds, like the lower bound method that we can use for Schiraldi-Adams, in order to separate PPP from its Turing closure. Okay, so how do you prove lower bounds on Schiraldi-Adams? So these are proven by constructing these dual objects called pseudo-expectations. So you can show that there is a D pseudo-expectation for this pigeon squared problem if and only if there's no degree at most D Schiraldi-Adams proof that the pigeon squared problem is total. This isn't particular for pigeon squared, it's for any unsatisfiable CNF formula, but I've just stated it for pigeon squared. So what's a pseudo-expectation? Let me first redefine expectations, like standard probability expectations, in terms of their moments. So you can describe any probability distribution uniquely by all of its moments. So a moment is the expectation over your probability distribution of some conjunct C. A conjunct here is just, a standard conjunction of things. And we're going to translate this into an algebraic world where, positive variables just become positive variables, negative variables become 1 minus that variable, and then you multiply them all together. Over 0, 1, these two things are equivalent. Okay, and so you can define describe a probability distribution uniquely by all of its moments. Here's each of the moments. This is like degree 1 moments, or sorry, they should be degree 0 moments. It's just an expectation of 1, and up there you have, all products of, or all conjunctions. And the main property that these expectations are going to satisfy is that they're non-negative on all conjuncts. All moments of probability distribution are non-negative just because probabilities are non-negative. Okay, and a pseudo expectation is only going to require this non-negativity on conjuncts of degree at most d. So something like this. We pick a d, we just chop it off here, and we just let it behave however it wants on things that are higher. So they can become negative up there. So more formally, a pseudo expectation is a linear map, which is normalized and is consistent with the distribution on all its low degree moments. So it's non-negative on everything, on every conjunct, which mentions the most d variables. And expectations are pseudo expectations, but the converse doesn't hold. There are things that, you'll see examples of these, things that are pseudo expectations, but not expectations of true probability distributions. Okay, so we have this dual characterization. It says that there's a d pseudo expectation for pigeon squared if and only if there's no Shirley-Adams proof. So what's an expectation for pigeon squared? So we're going to say that a conjunct witnesses a particular assignment x. If x is the unique assignment to the variables of that conjunct, which makes that conjunct output 1. So the thing that just sets all the variables in the correct direction. So I'm going to be using n-ary variables here. I'm going to use this notation. It's somewhat standard. So this is the conjunct that says that pigeon 1 has to be mapped to whole 2. You can encode this in binary by representing this by like log n many variables to put it in a binary representation, but it's nice to work with this n-ary stuff. So this conjunct witnesses the assignment that pigeon 1 goes to whole 2, and pigeon 0 from the second instance goes to whole 3. So I'm going to denote these by p's and these by q's. This is what this conjunct is witnessing. Yeah, and interrupt me if there's any questions or anything like that. Something doesn't make sense. Okay, so an expectation for pigeon squared is an expectation whose support is only on bijective maps from pigeons to wholes, or like it never maps 2 pigeons to the same whole or a pigeon to 2 different wholes. So in particular, if a conjunct witnesses a solution to pigeon squared, then this expectation sets its value to 0. So it's not a support. So if we had something that mapped these two to this, and these two to this, or something like that, then this conjunct would receive 0 mass under the expectation. Yeah, and by witnesses a solution to pigeon, yeah, I just mean that the conjunct sends 2 pigeons to the same hole in both instances of pigeon. Okay, something like that. Yeah, for example, the conjunct contains this like a subconjunct, these 2 things. Yeah, and you can already see that there's no one of these expectations for pigeon squared doesn't exist because pigeon squared is a total function. There's no probability distribution over maps from n pigeons to n-1 holes, for example. Right? The probability distribution would have to set everything to 0. Okay, but what we're going to show is that there is pseudo expectations for pigeon squared. So remember, this is our definition of a pseudo expectation. And a pseudo expectation for pigeon has this additional third condition that if our conjunction C has degree at most D, and it witnesses a solution to pigeon squared, that is, like, as a subconjunction, it sends 2 pigeons to the same hole in both of the 2 instances of pigeon, then it receives 0 expectation under this. Yeah. So Shirley-Adams can't prove the totality of pigeon or pigeon squared. Like, there's a lower bound for the pigeonhole principle for Shirley-Adams, which means that there is a polylog n degree pseudo expectation for both of them. So regular pseudo expectations lie here. They separate Shirley-Adams or PPADS from PPP. So what this means is we can't use regular pseudo expectations in order to separate pigeon from its Turing closure. So the idea of our lower bound technique is to strengthen the idea of a pseudo expectation to distinguish between pigeon and pigeon squared. So we want to generalize pseudo expectations. We're going to define this notion of a collision-free pseudo expectation so that it lies, rather than being in between these two, it's going to lie in between these two. There is a collision-free pseudo expectation for pigeon squared, but there's going to be none for pigeon. So so we'll define this operator, and then we'll show that if we can prove that such an operator exists, then it implies the separation that we want. Okay, so throughout this talk, I'm going to make a small simplifying assumption that's just going to make it easier to talk about all of these decision trees in our reductions. So this is like the standard picture of a reduction. We have a set of n+1 decision trees mapping an input to pigeon squared to pigeon, and then for each potential output, we have a decision tree mapping it back. I'm going to assume we don't have these output decision trees. We just have these input decision trees. It'll just make it, they're all polylog depth. It'll just make it easier to talk about things throughout. Yeah, so there's no output decision trees. So it just looks like this. So in particular, if you get a solution here, then you don't need to query any additional variables to know what solution you would get for the pigeon squared problem. And this can be sort of summarized by the following correctness property. So if we found 2 pigeons which map to the same hole in this, defined by this reduction, then X, like the input to pigeon squared, has to contain a solution to the pigeon squared problem. Previously it was, if this happened, then Tij of X would map it back to a solution, but I'm just going to assume X contains a solution as like a subconjunction. Yeah, just makes it easier to talk about. It's like just a little bit of like extra work to like put these in.
So like the collision in the pigeon instance is going to be a collision in one of the 2 instances that you have in parallel in the other. Is that the idea?
I'm not sure if it's formally like that. Well, it would just be that like if this pigeon I and pigeon J collide here, then this X here, this assignment X would actually have 2 collision. Would actually have 2 pigeons.
You're
Yeah,
supposed to
for
output the
definition totality.
Yeah, sorry, maybe I mean something different.
Sure.
The definition of totality.
Yes.
But you were asking whether you should output both pairs or
No. So what I was
No,
asking
no,
is
yeah,
like
yeah,
if-
that's a
So
good
on
point.
the left you have like the two instances of pigeon. Then you reduce it to one instance of pigeon. You get a collision, and I was imagining that from that collision would already inform a collision either the left or the right in the original.
Yeah, sorry, it should be the variables queried by TI and TJ contain this thing. So in particular, you don't need to query any additional variables. That's what I want to say. Yeah, thank you. Yeah, so these things each query polylog n variables, and then the variables, this should actually be that, yeah, the variables queried in these TI and TJ witness a solution to the pigeon square thing. So these things actually see pigeons in, one collision in each instance of the pigeon. Does that make sense? I can repeat that again if it doesn't, because this is not exactly. So just X restricted to the variables queried in these two decision trees actually contains, you actually see a solution to this. Previously, you'd have to query some additional things defined by this to see.
But there's still some tree that only queries those variables, but that's the computation.
Well, yeah.
Like given, like when you say that it contains, like how do I extract it?
Oh, you would just read it off from those those variables,
okay.
like a decision tree. You just think about it as learning some information about some coordinates, and then you do some magical computation outside.
Okay.
Now you don't need to learn any additional information. You just what's contained in these two decision trees.
Sure.
Yeah, good question. Thanks for the clarification. Okay. Yeah. So now we want to define this extended version of a pseudo expectation. So pseudo expectations separate PPADS from PPP, or equivalently Shirali-Adams from pigeon. We want to strengthen it so it separates pigeon from pigeon squared. So what we're going to do is we're going to look at pseudo expectation. We're going to add on an additional condition, which is going to make it a bit stronger. And in order to figure out what this condition should be, we're going to first suppose that we have a reduction from pigeon squared to pigeon, and we're going to extract the property. By looking at such a reduction, we're going to extract the property that we would need in order to contradict the existence of such a reduction. So suppose there's a reduction, we're going to look at what we need in order to get a contradiction from that. Yeah. Okay. So for each of these decision trees, we're going to look at the root to leaf paths in them. And and we're going to think of each root to leaf path. A root to leaf path in a decision tree names a bunch of variables and sets them either to 0 or 1. These are equivalent to conjuncts, basically. You can take the and of all the literals queried on the path, where you take a variable positive if you went to the one side and a variable negative if you went to the 0 side. Okay, so we're going to think of each decision tree PI as a set of root to leaf paths. And each of these TIs, this decision tree TI, tells me where pigeon I maps. So I'm going to define Hij to be the set of all paths in this decision tree which map pigeon I, so TI maps pigeon I, to whole J. So Hij is, the subset of this that says pigeon I maps to whole J. Okay, and then I'm going to say that Hj is the union over all I, and so Hj is just going to be the paths which send some pigeon, the paths in all decision trees, all of these T1 to Tn plus 1, which send some pigeon to whole J. Okay. And the key property is that if you look at this set of all these paths, then any pair of paths in them are either inconsistent, meaning they map two pigeons, they map one pigeon to two different holes. Their conjunct is formally 1, equivalently, or they're pairwise witnessing. So if you take the and of these two conjunctions, then they contain a solution to the pigeon squared problem. So I claim that this property holds. And this is just going to follow by correctness. Okay. So it's pretty easy to see. So we want to prove this key property. So take any two paths in this HJ. So two paths that map some pigeon to whole J. Then if these two paths are from the same decision tree, we know paths from any decision tree are inconsistent. Oops, sorry. Yeah, so so paths from any decision tree are inconsistent, right? So if you take like a decision tree query X and you either set it to 1 or to 0, these two paths differ on X. That's all I mean by this. Okay, so suppose that there's a pair of conjuncts or paths in HJ such that neither of these hold, and I'm going to get a contradiction to this. By the observation, we know that they have to come from two different decision trees, TI and TK, for such that they're not the same. We know that they're both in HJ, which means that they output, that these paths send, sorry, this should be TI. What I'm saying here is that they both of these paths map pigeons to, so this should say that PI and PJ go to whole J, just because they're in H. That should be K. So if I take any two paths in HJ, these tell me that two pigeons map to whole J, right? They come from different decision trees because otherwise they'd be inconsistent. We suppose that they're not inconsistent. So now we have found these two paths have to be a solution to the pigeon squared problem, to the pigeon problem, just because they're from HJ. But since we assume that they're not pairwise witnessing, that means we have that the and of these two paths is a solution to pigeon, but not to pigeon squared, and this contradicts that this was actually like a valid reduction from pigeon to pigeon squared. So we have this key property here. Okay? And we're going to use this key property in order to define our extended version of a pseudo expectation. Okay, so I'm going to define what a pairwise witnessing family is. It's basically just our HJ, but like extended, like the definition is just going to be kind of generalized. So any collection of degree at most D conjuncts is a pairwise witnessing family if each pair of conjuncts in this collection is either inconsistent or pairwise witnessing. So in particular, one of these HJs was, is a pairwise witnessing family. And then our extended version of a pseudo expectation. So here we have our regular version of a pseudo expectation for pigeon squared. And we're going to add on this collision-free thing. So this last property is going to basically say that for each of these, I'll show it to you in a minute, but it's going to basically come from the upper bound on the standard upper bound on proving the pigeonhole principle. We're going to sum up the number of pigeons, sum up the number of holes, and if we have this additional condition, that this is going to say that at most one pigeon maps to each hole, this is going to allow us to get a contradiction. Okay, so let's see this. So I claim that if there's one of these collision-free pseudo expectations, then there's no reduction from the Turing closure of PPP to PPP. Okay, so suppose otherwise. Suppose there is a reduction from pigeon squared to pigeon, and let T1 to Tn be this reduction. So now let's look at one of these decision trees, Ti, and let's sum over all root to leaf paths in this decision tree. We know that if you sum over all the root to leaf paths in a decision tree, it's just a formally one polynomial. You can see that here, right? So yeah, well, nothing here is dependent on my definition of a pseudo expectation yet. Now I'm going to apply my collision-free pseudo expectation to both sides. By the fact that it was normalized, the expectation of 1 is 1. By linearity, I can move this expectation inward. And now I'm going to sum over all pigeons. Maybe this should be n plus 1. I think I'm going to be switching accidentally back and forth between n and n plus 1. So summing over all the pigeons, we get this. Now I'm going to partition this sum according to the holes. So I'm going to look at all paths here which map a pigeon to hole j. So I have this here. So hj is just all paths which map some pigeon to hole j in one of these decision trees. And there's at most n minus 1, let's say. There's n pigeons, n minus 1 holes in what I've written here. Yeah, so I'm just rearranging things. Nothing has been done there. And we know that this is pairwise witnessing, right? So by the final property of my collision-free pseudo expectation for any pairwise witnessing family, its expectations at most 1. Yeah. So this is the final property here, and this is going to give me a contradiction. This left side is n, right side is n minus 1. So what this pairwise witnessing, this collision-free property here is saying is that in such a reduction, no pigeon maps to, like, each hole receives a mass of at most 1 pigeon. Okay, so that gives a contradiction, and it remains to construct one of these collision-free pseudo expectations. Yeah, so is there any questions at this point? Anything that I can clarify? Yeah, so this was our definition of a collision-free pseudo expectation. So we have this final property, basically says that each hole in the pigeon instance receives a mass of at most 1 pigeon. And so we want to construct a candidate. Yeah, so it remains to show that one of these pseudo expectations exists, and then as we proved, if it exists, then there's a separation between pigeon and pigeon squared. So how are we going to do this? So there's a standard pseudo expectation for pigeon. This there's lower bounds for the pigeonhole principle for Shirley-Adams. This defines a pseudo expectation for the pigeonhole principle. We're going to take that same pseudo expectation and we're going to plant it on the 2 different instances of the pigeonhole principle that we have in this pigeon squared problem. And then that's going to satisfy these top 3 things because it's a pseudo expectation, nothing special there. And then we have to verify that it satisfies the 4th property. Okay, so here's the definition of our collision-free pseudo expectation. So for any conjunct, I'm going to partition it into 2 parts, C1 and C2. C1 is going to be the part that mentions the variables from the first instance, and C2 is going to be the part that mentions the variables from the second instance. So C1 is going to be like P0 goes to H1, P1 goes to H2, yeah. And C2 is going to be the part that mentions the Q variables and the holes for this. Okay. And then for this conjunct, so I'm going to define the value of this expectation. This expectation is an operator from polynomials to reals. So I have to define a value for each, the value of this operator on each polynomial. It's linear, so I can define it just on conjuncts. Yeah. So if this conjunct is not a matching, so if it maps two pigeons to the same hole or a pigeon to two different holes or something like that, I'm going to set the expectation to be 0. This is going to satisfy this non-witnessing property. You know, we don't want it to see a solution to pigeon squared. If it is a matching, then I'm just going to set the probability, like the expectation of this conjunct, to be the probability of uniformly at random choosing that matching. So if I have like this pigeon, if I have this particular matching here, I'm just going to set, I think I actually do the calculation here. Yeah, so this is what it is, but it's the probability of that I have that these pigeons went to these exact holes uniformly over all possible choices of the 3 holes that I could have gone to.
I think you need the charger.
Yeah. Does somebody have? Do you have a charger with you? I have mine upstairs.
Can you take this in some window?
Yeah. Yeah. So now's a good time for any questions. So,
Maybe inside the car. Or inside there, the box there, there's an extension, I think.
The white thingy.
Does not seem to extend very far, but
Oh.
they should be fine. Okay. Yeah, so it's just going to be probability of uniformly choosing this matching. So that's what it is formally. In this example, it's easier to see. So it's the probability of this conjunct witnessed here is going to just be this value. So you can see it's the probability that P0 goes to hole 1. That's a, should actually be a third, sorry. Check this. Okay, so 1/3, 1/2, 1/. What have I done here? Okay, so maybe if you imagine this one going here, okay, maybe I'll draw a picture on the. So this one should be 1, 2, 3, 4. 1, 2, 3. And the probability of something like this, and Q1, 2, 3, 4. 1, 2, 3, and maybe like this, something like this. This particular conjunct would be the probability that P1 goes to H1, and this is the third. Now, given that P1 goes to H1, the probability that P3 goes to H2, which is half, because there's 2 holes left, then times the probability that Q3 goes to H1 here. I haven't set any of these, so it's just a third. So something like that, just uniform the problem.
So this one would be 0? Like
Uh,
C1 one, because both are going to
Yeah, so
H2?
this one would be 0, yes.
Okay.
This one's 0. Yeah, for some reason that got a typo on it. But if this one went over here or something like that, then it would be a third times a half times 1.
Okay.
Yeah, so just uniform probability of this matching. Okay. So you can observe that we satisfy these three properties. The expectation of 1 is 1. It's non-negative for all degree at most d conjuncts. This basically follows, well, it follows by our definition here. So, you know, uniform probability is non-negative, and 0 is non-negative, so that's good, and this is defined for all degree at most d conjuncts. For higher degree polynomials, we just define it however, it doesn't matter. And it's non-witnessing by this first property. Okay, and it remains to prove this collision freeness.
Can you say anything more about the first three properties are just the standard, like where I
Exactly.
want to say, okay, contradiction maps to one, and the like low degree, sort of, what are they called? Generalized monomials or whatever are non-negative, and then basically anything multiplying an axiom is goes to zero. That's like item 3, right?
Exactly. Yeah.
So again, item 4, any for summing over C's in a D pairwise witnessing family.
Yeah. So this is like. Yeah, so remember the pairwise witnessing family is a family of conjuncts such that if you take any two of them, you AND them, they're either inconsistent, that's fine, they're formally the one polynomial, or together they witness a solution to this pigeon squared problem. Then I'm going to want this expectation to be at most 1. And the reason, what this is saying is that if I use this in a reduction from pigeon squared to pigeon, then this is saying that each whole, so yeah, so, yeah, this is a good question because these things are a little confusing. So this is where we got our definition of pairwise witnessing, basically. So if we use one of these things in a reduction from pigeon squared to pigeon, it's going to say that each whole receives the mass of at most 1 pigeon. So I'm trying to do the like standard upper bound, say like cutting plane's upper bound or whatever, on the pigeonhole principle. You sum up the number of pigeons, you sum up the number of holes, and you get a contradiction. So this is what a D pairwise witnessing or a collision-free pseudo-expectation is saying, is that for any pair of conjuncts which witness for any set of conjuncts which map pigeons, for any set of conjuncts which witness pigeons mapping to the same whole, then the mass of that set of conjuncts is at most 1. So yeah, so we're working over the variables of this pigeon squared problem. But if I plugged these variables into my decision tree and I saw like, that they told me that, that they sent a pigeon to some whole J, I look at all the partial assignments that sent a pigeon to whole J, then the sum of the mass of these pigeons is going to be at most 1. So I want to say that each whole receives mass at most 1. Yeah, so maybe I can say it a little bit more concretely. So we have this reduction, T1 up to Tn plus 1, from pigeon squared to pigeon. This reduction is a bunch of decision trees. Ti tells me where pigeon I flies in just the instance of pigeon, but it's querying the variables of pigeon squared. And this decision tree has leaves, so it has leaves labeled with holes. So this is like Ti, and this is like hole 1, hole 2, maybe it's hole 1 again, something like that. And so I query these variables. It's querying variables to pigeon squared. And it's telling me where does the ith pigeon in the instance of pigeon fly to. Here it's flying to hole 2. And if I look at all of my decision trees, and I collect all of the paths, all of the partial assignments that would have sent a pigeon to hole 2, then the total mass of all of these paths can be at most 1. That's what I'm saying. And that's enough to give you a contradiction, because now the total mass of my pigeons is going to be n. There's n pigeons, but the total mass of my holes is n minus 1. And that's what's happening here. Yeah, does that make sense? Or
I think it makes some sense. Maybe I just need to meditate over it a bit. But
yeah,
is it true that so if we go back to this fourth item, well, just to that sort of it, you're saying, should I think of it in the way that this fourth condition, in order for it to make sense, I have to hypothesize that I have one of these impossible reductions,
yeah,
and somehow plug it into the reasoning, and 4 talks about, because the other 3 just, I guess, talk about,
yeah. So
they just talk about the problem. No?
Yeah. The fourth one kind of comes from one of these hypothesized reductions. So you can see, you can talk about it unrelated to one of these reductions.
Mm-hmm.
But, well, yeah. It's one of these pairwise witnessing.
Okay.
So if you take the and of the 2 conjuncts, yeah, so a pairwise witnessing family is like a set of conjuncts such that if you take the and of any 2 of them, they're either inconsistent, they're the one polynomial, or they witness a solution to pigeon squared. So they actually see, they contain the partial assignment corresponding to the conjunct, like the partial assignment that satisfies this conjunct, the unique one, sends 2 pigeons to the same hole in both instances of pigeon, like in the pigeon squared thing. So it contains that as like a yeah. For each conjunct corresponds to a partial assignment. That partial assignment is either a matching, which is good. We don't see any solutions to any violations to the negation of the pigeonhole principle, or it contains a collision. And if it contains 2, so if something's pairwise witnessing, if for every pair of conjuncts you add them together, they contain these 2 collisions. That's a little tricky.
Is it obvious that this is linear? We have a question from the audience.
Is it obvious that this is linear?
The operator that you...
Oh, yeah. So we defined it on conjunctions and extended it linearly. One cheap way to see that this is going to be linear is that this pseudo expectation that we defined is exactly the pseudo expectation that one uses to prove like the lower bound on the pigeonhole principle for Shirley-Adams. We just producted it. We took 2 copies of it. It should be linear, like one way to see it. So here's the definition. You can see that it's linear by just summing up. If you sum up over, like you can marginalize out a particular query to a pigeon by summing up over all the possible ways it could go. Does that make sense?
So you define it on conjuncts, and therefore it's linear, and now that by definition, right?
Yeah, because
you
it's
define it on,
it is, but then you have to check that it like is consistent over marginals.
which would
But
be
that's
the
just
same
going
thing as Boolean axioms being 0.
Yes. Yeah.
Or
Yeah.
think
Yeah.
of it other Boolean.
Yeah.
Okay.
Yeah. I think it's also by the fact that we just assigned a uniform probability here. So the marginals of this thing.
Okay.
Yeah. Does that answer the question, or should I say a bit more?
I'm looking at the chat to see if it answers the question or not. I guess so far so good.
Okay.
No reaction. I'll let you know if cyberspace has any objections. So far, I think we can proceed.
So I'm just going to say
Also, like,
yeah.
go back to one slide. No, the calculation.
the
also-
calculation's wrong. So
No, I think the calculation is right.
Oh,
I think the calculation's wrong because of these. two.
No, because you want it to be a matching, so you want the whole to choose pigeon, not the pigeon to choose the whole. So the calculation here is right. The one on the board is now wrong. Is wrong because you want it other way around because you define it C1 and C2 is a matching, so you have to like the whole choose the pigeon, right?
Sorry.
You want it to be a matching, right?
from
yeah.
host, so from host
So the
to
host
pigeon
to
or
have to
from
choose the pigeon. If the pigeon choose the whole, it may not be a matching, right?
If it's
So
You want a whole to choose the pigeon, so it's 1/4, 1/3, 1/2, 1. So that's a correct one. Yeah. And
All can choose multiple pigeons.
no, whole can choose one pigeon.
but then
So-
you have
but
like,
So you have, but in this case, like the first hole has 4 options for pigeon.
Yeah, but
And-
all two chose P1 and P3.
No, it's just one.
no. So
One
I
option.
think you fix the pigeons here, and then you want to choose the probability of those pigeons going to picking out the holes.
So it's
Yeah,
not
but
like
Oh yeah.
okay. So you fix the pigeon first, and then
Yeah.
you choose
Yeah.
okay.
It's the probability of choosing this particular matching. Now this one should be going somewhere else. I think this was supposed to be an example of the first one, and I just
I thought it's like for the explanation
Mhm.
for this one, I thought it's like you're just fixing the hole or something, like you choose like which pigeon goes to this hole.
no.
No,
So
then because you uniformly choosing over all the matchings, right? That's the same.
yeah.
So
Sorry.
you have completed all the matchings.
Yeah, I should have been a bit more careful with this. So it's uniformly choosing. So you fix the pigeons and then uniformly choosing the probability of choosing this particular matching. So just ignore this one, and then over here it would be like the probability. I have these 2 pigeons fixed, and I want to say what's the probability that I get this matching on these pigeons, as opposed to like this one and this one or something like that. And that's going to give you this probability here. Yeah, probability you match it to the first one, and then these guys are fixed. You have 2 choices for this. Yeah. Okay. So I'm
We
basically
should probably try to wrap up the first part at some point now.
yes. Yeah. So I'm basically done. Yeah. So the last thing we need to do is verify this new condition, this collision freeness, that each hole gets mass at most 1. And the high-level idea here uses some techniques from proof complexity, in particular, the pigeonhole principle lower bound for AC0 Frege. So what we do here is we have one of these pairwise witnessing families, F, and we want to prove that the total mass of this pairwise witnessing family is at most 1. That would verify this collision freeness property. What we're going to do is we're going to take this family and we're going to build this thing called a matching decision tree. This comes from this AC0 Frege paper. And this matching decision tree kind of covers F. So it's like we're going to take this family. The family is a set of conjuncts. Equivalently, it's a DNF. And we're going to build a decision tree which covers this family, or like represents this family. And then we're going to show that the expectation of the decision tree is an upper bound on the expectation of this family. So now we have turned the problem of upper bounding the expectation of a pairwise witnessing family to bounding the expectation of one of these matching decision trees. And then the actual bound is a very careful decomposition of this decision tree. So that's all I'm going to say for now. I can actually go into some of the calculations after the break. Yeah.
Thank you. Any more questions before we take a break? From anyone, or should we just and let's thank Noah again. So we are back after the break to hear more about the exciting technical details, or at least some of them.
Yeah.
The wise guidance of continued wise guidance of Noah.
Yeah. So maybe I can give you a little bit more intuition on this, like reduction for this collision-free pseudo expectation. This where these pairwise witnessing families are coming from. So, like, suppose that you have a reduction from some problem to the pigeon. We want to say that this reduction is not correct. So for the reduction to be correct, we want that whenever you have like an input to your problem, then the thing you get out, like the instance of the pigeon problem that you get out, has to have two pigeons colliding, right? Otherwise, it's not a correct reduction. So what this pairwise witnessing family is saying is just like, you can think of a pairwise witnessing family as being roughly a family of conjuncts that are all looking at whether whether one of these collisions happens in like hole I or something like that. And we're just going to say that yeah, so if the mass, like the probability, were given to having these, like, if the probability of one of these pairwise witnessing families is maybe start again. Yeah, so a pairwise witnessing family is like kind of trying to witness whether there's a solution in hole I. So whether two pigeons map to the same hole. So we take a reduction from some problem to pigeon. We look at all the paths in decision trees which would map a pigeon to hole I, and we want that the total mass of such a family is at most one. Essentially, this is saying that at most, for hole I, at most one pigeon is mapping to hole I. And we want to contradict the existence of this reduction, right? So if at most one pigeon maps to this hole, and we have that for every hole, then there can't be, there's no solution to this pigeon problem, and therefore the reduction could not have been correct. That's kind of where the intuition for this is. So we're trying to say that every hole gets at most one pigeon in this reduction. The reduced instance, in the reduced instance, every hole is getting at most one pigeon. That's what we're trying to say. And then if that's the case, we just do the standard pigeonhole upper bound. We sum up the number of pigeons, there's n pigeons. We sum up the number of holes, there's n minus 1 holes, which we see that this is a contradiction. Is that good? Is that...
Again, just to understand what the pairwise witnessing family is, it's the conjuncts in the family. Firstly, if any conjunct in itself was not a partial matching, then it would already be sent to 0. So that somehow that we're picking out the family contains the only interesting families, I guess. They contain partial matchings, but then so you have like a collection of partial matchings, but they have the interesting property that whenever you take any two partial matchings and say I want both of them, then you're solving both.
Then I'm solving the problem that I'm reducing to pigeon. So we have a solution to the original problem. So what we're trying to say is we get a solution to the original problem, but we don't get a solution to pigeon. So in one of these, witnesses should witness a solution to pigeon. It witnesses a solution to pigeon squared, and we're trying to say it doesn't witness a solution to pigeon. So it assigns mass at most one to, essentially at most one pigeon is being mapped to hole J. We have a solution to the problem that we're reducing to pigeon, but at most one pigeon is going to each hole in this thing. By at most one pigeon, I mean that the mass that each hole is receiving is at most one.
And you're going to do this for all shallow trees, are you?
Yeah.
So I was slightly off before when I said that you have to hypothesize a reduction and the lower bound is based on that. The lower bound is much stronger in the sense that you, like,
For
again,
any
items
reduction,
1, 2, 3 would be the standard thing, but then you say, okay, for anything that could possibly be a reduction,
Exactly, yeah.
namely it's like so any conjunct that would result from these shallow decision trees, in addition to all the other constraints I have, let me also impose some technical conditions on those. And then if I have those technical conditions also, that is somehow giving us what we want.
Yeah, so basically for any possible reduction from some problem to the pigeon problem, this reduction is failing. This reduction is not witnessing a solution. We get a solution in the problem that we're reducing from, but not a solution in the pigeon problem, the thing we're reducing to.
Okay, should we maybe have more questions, or should we just try to charge ahead and see how far we get? Or what's the plan?
Yeah. Is that clear, or is it? So this one's saying that there is a solution to the problem that we're reducing from, but then we're gonna force that the mass of this thing is at most one. Essentially, what it's saying just is that each hole is receiving at most one pigeon, and so we're not seeing a solution in the pigeon instance. We're seeing a solution in pigeon squared, but not in pigeon. Therefore, this reduction is wrong. So any reduction we plug in, it's going to break if this pseudo expectation exists. Yeah, and you can see it in this calculation here. So you have n pigeons. You take all paths which map to hole J. Each of these things receives mass at most 1. And so you're going to get at most n minus 1 here, or maybe that's n plus 1. Is it, yeah. So anything more I could say about it, or do you want me to continue?
I think you should continue.
Okay. Okay, so the last thing is to prove that the expectation of any of these pairwise witnessing families, paths and decision trees that together map two pigeons to the same hole, are consistent and map two pigeons to the same hole. That the total mass of this thing under our expectation is at most 1. And the way we're going to do this is we're going to build a decision tree that captures one of these families. Basically, it's nicer to analyze decision trees than it is to analyze DNFs, or sets of conjuncts. So we're going to build one of these things that upper bounds the mass of this family, and then we're going to just analyze this tree. Okay, so what's a matching decision tree? So it's a decision tree where every vertex is either labeled by a pigeon query. So we query one of the pigeons from one of the two instances of pigeon, and we fan out over all possible holes where that pigeon could go. Or we do a hole query. So we pick a hole and we fan out over all possible pigeons that could go to that hole. Something like that. Okay. And then the leaves are labeled either 0 or 1. Basically, the ones that are labeled with 1 are going to be the ones that are consistent with the conjunct in our family. And any root to leaf path here is going to induce a matching of pigeons to holes, or
And the alternations between pigeons and holes, that's arbitrary.
yeah, we're just
I'm
gonna
gonna have pigeon paths or hole paths or every second, or who knows what will happen.
Yeah, I'll give you a general procedure for defining this thing.
Okay.
There's not going to be a particular alternation, but hole queries are going to be the problematic ones. Pigeon queries are going to be fine.
Okay.
Upper bound of the expectation. It'll be a matching just because we're never going to if I query pigeon 0 and map it to hole 1, I'm never going to query. This is probably not me.
Okay.
Hole 1, maybe this should be hole 2.
You never do what is it.
I'll never do this.
One.
Yes. I'll never repeatedly query things. I'm gonna just make sure that it's all a matching just by construction. It'll be
Okay.
fine.
And then when you fan out, you only fan out on things that
On things that have not been
not been
queried.
queried.
Yeah. So I'm just gonna make sure it's all a matching. It's gonna be
And
nicely
then
behaved.
labels 0s and 1s correspond to what?
So I'm going to label it 1 if it's consistent with one of the conjuncts in my family. I'll tell you how to do this in a minute. And 0 if it's not.
Okay.
Then I'm just going to care about the mass on the 1 paths. Okay. And the expectation of the tree is going to be the sum over the expectations of the 1 paths, or the conjuncts corresponding to the 1 root to leaf paths in this tree. Okay. And we're going to say that a decision tree T covers one of these families, a family of conjuncts, if for every conjunct there's a unique root to leaf path labeled 1, which contains this conjunct as like a sub-conjunct. Okay. I queried, maybe my path was just, or maybe my conjunct was just pigeon 0 goes to hole 1 or something like that, then any of these things would be consistent with it.
Okay, but you want there
If
to
this
be a
thing was
unique
different
one.
thing. Yeah. Yes, unique one labeled 1.
Oh,
Yeah.
labeled 1, okay.
Yeah. Yeah.
And why unique? Is that just to
I don't
maintain
actually
a
think
handle on the weights, or?
Yeah, so the next inequality is true, right?
Yes. Yeah. Sorry, this should be backwards. Should have really reviewed these. Yeah, I don't actually think I need this unique property, but
Oh,
so I want this to be reversed. So I want that if it covers it, then the expectation of this thing is going to be at most. Expectation of F.
Should be the other way. I mean,
Yes, it should be the other way around.
It seems like if you have uniqueness, you would get this maybe. If you
Yes,
don't,
yes,
yeah,
yes,
then
yes,
the-
good.
In the previous slide, you had it the other way.
Yes, it should. Sorry, yes, it should be the other way around. Yeah,
You want the upper bound.
yeah. So I want to upper bound this because I want to say this is at most 1. Yes, good. I need the uniqueness in order to make sure that this upper bound holds.
yeah, let me see why this is the case.
But then you just need at least one, right?
Mm,
Well, it makes sense that you would want uniqueness to maintain control over the weight of t. Because if you have like massive overcounting, then I'd get worried when you want to start. But for the inequality,
For the inequality.
For the
Yeah, the
inequality,
inequality should be
f
at least
less equal t, I don't see that you need uniqueness.
Yeah.
But like you want uniqueness probably to get control over t in the next step.
Yeah.
Also, can I, like,
I
there are,
feel like we won't actually need. Sorry.
so indices,
Mhm.
there can be negative
Indices.
negations,
Oh
Right.
yes, yeah,
and then you
yeah.
could just take any path where it doesn't go to the
Oh yes, sorry. So
thing.
yeah, so that's like a little bit of a confusion moving between n-ary variables and 0, 1 variables.
okay,
So
okay.
in the n-ary variables, you're not going to have the
Right,
negations.
sure,
Just the
sure,
Boolean
yes, of
encoding,
course.
you're going to have the negations.
Yes. Okay.
Yeah. So n-ary variables, yeah, it's just matchings.
Right. Okay.
Yeah. So the canonical matching decision tree. Yeah, I don't actually think. Yeah, so we're going to build for each family F. We're going to build a decision tree recursively. Or sorry, for each family of conjuncts, we're going to build a decision tree recursively as follows. We're going to think of this F as being a DNF, and then if currently my family is just falsified, like it's a false DNF, I'm going to label the leaf with 0. If it's satisfied, I'm going to label the leaf with 1. And otherwise, I'm going to pick a conjunct, and I'm going to query all of the pigeons and holes mentioned in this conjunct. Yeah, I actually don't think I need this uniqueness property. Sorry, I don't. So what we're going to do is, yeah, pick a conjunct. This conjunct mentions some pigeons and holes. I'm going to query all of them, and then I'm going to recurse at each leaf. So I can do a little example. So if I have this conjunct here, so pigeon 1 goes to hole 1, pigeon 2 from the second instance goes to hole 1, and pigeon 1, so that's the first conjunct. The second one just has pigeon 1 going to hole 2. Then I query pigeon 1. So I've queried pigeon 1, and I sent it to hole 1 here. So that's those pigeon 1 and hole 1 have been covered. Now I've left hole 2 the second hole 1 and the second pigeon from the first instance. This one gets a 1 because I've satisfied this conjunct. And then I continue querying like this. So these ones falsify this conjunct here, and they also falsify this. There's no matching consistent with both of those. If I've done it correctly.
Could you just as well query Q2 after
Oh, yeah.
the first one?
Yeah. There's no order to this.
Okay, but why do you need the whole queries then?
Why do I need the whole queries?
Coordinate on big video queries.
So I don't. Yes, good. So, but. So I think one problem is that the decision tree might have very large depth. Yeah, yeah. Right, because if I query so completely blanking on this.
It says there, it says there, query each of the pigeons and holes mentioned in C.
Yes.
So do you query each of them? So would you query P1 and H1 one, like because it's mentioned? Because I got
but here, yes, that's good. So, but we're not going to query it here because we want it to be like, we could do it here, but then we would
only have one outgoing.
Yeah, one outgoing labeled 1, I guess. It would just be kind of like a redundant thing. So I've just kind of shortened it here.
Okay, so maybe you wouldn't need to query both if it's already known.
Yeah.
Okay.
Yeah.
So in this shortening, maybe it's okay to only query pigeons because I don't know.
It should come from the fact that we're working with pigeons squared. Why you need to worry about these whole queries. No, maybe not. Yes, sorry, it's really important that you need to. It's a good question. I'm completely blanking on it. Because the pigeon queries are not actually going to be much of a problem for us. The whole queries are going to be a huge problem.
Okay.
So let me remind myself. And it should be bounding the depth of this thing, I think. Yeah, sorry. Yeah, so that's a good question. So later we'll use it. Right, so one of these families can be a pairwise witnessing family is a family such that, like either any pair forms a solution or is inconsistent. Now they can either be inconsistent on the pigeons or the holes. And if you just query the pigeons, this decision tree may become really, really large. We'll see this a little bit later.
So if you had like the different conjuncts, like pigeon 1 goes to hole 1, or pigeon 2 goes to hole 1, or pigeon 3 goes to hole 1. These are like all the different conjuncts in your family.
Yeah.
And then you can just query hole 1, and then your decision tree would be done, or you have to query like all the pigeons.
Yeah.
So
Yeah.
in one case you get something.
So yeah, so I think the intuition is that later on, so if we don't have 2 instances of pigeon, we just have 1 instance of pigeon, and they're all inconsistent, then that means that if I query, or maybe my family is just entirely inconsistent. Let's just think about that. Then that means that all conjuncts in my family overlap on some pigeon or hole. So that means if I can bound the depth of this decision tree by querying pigeons and holes. Every time I query one conjunct, I'm gonna, since it intersects with every other conjunct, I'm gonna decrease the width of every other conjunct by at least 1. And so I'm gonna repeat this process at most the width of these conjuncts many times. So that's why we're gonna use these hole queries. Yes, very, very good question, very crucial, because yeah, I'll show you in a minute that this is going to be a problem. Okay. So yeah, so we want to bound the expectation of this thing by the expectation of this matching decision tree that we built by 1 for any pairwise witness in family. And remember, the way we built this matching decision tree is we just repeatedly picked conjuncts in our family and queried all the things, all the variables in the conjunct until we've covered them all, basically. All the pigeons and holes.
Oh, and it's this layered thing, right? Or no? Is it this layered thing that you always have all queries, or no?
You mean like oblivious?
Oblivious, yeah.
No, I think it could be different.
It could be different.
Yeah, it could be different because you may send, when you query a pigeon, you send it to some hole, and it depends on which hole you send it to. It could affect other ones. Okay. Yeah. So the challenge with bounding this. So this is why I really wanted to answer your question, because if you have a pigeon query, it's fine. You're not actually going to increase. You couldn't increase the weight above 1, right? So pigeon query has we set the mass of each thing like this to just be 1 over n. If we haven't queried anything, the mass of just this singleton conjunct is just 1 over n. Just how we defined it. So there's n of them, and so the entire mass is 1. So that's good. So it still keeps so if this is just our tree, the mass is at most 1.
Right, but the holes don't necessarily.
Yes, the holes are going to be the problem. And similarly, if we've already queried a bunch of things, pi is just some path in this tree, then the expectation is going to be this. This is how many things we've queried. There's n minus size of pi remaining things that you could fan out to, because we've queried pi many things going down here. And yeah, it's going to be fine. We're never going to increase the expectation in the pigeon queries. But the hole queries are going to be a problem, because there's n plus 1 things it could fan out to. And so the expectation of this thing is greater than 1. Okay, so that's a huge problem if we want to bound this by 1. And so what we really need to use is the fact that our the decision tree, the matching decision tree that we built, came from one of these pairwise witnessing families. This is going to allow us to bound the to say that, okay, if this happens, if we do one of these hole queries, a bunch of these things are going to have to be labeled with 0 if they're going to be consistent with a matching decision tree. So you do the same thing if you continue on downward. Expectation could exceed 1. Okay, and you can make the following naive bound on the expectation. if we know that the depth of the tree is small. This is where we're going to use the fact that later on we'll use this naive bound, and this will rely on the fact that that we use both these whole and pigeon queries.
Where did this bound come from? Sorry. Are you
Oh,
going to prove it?
I'll
or-
prove
Okay.
it. Yes, it's simple. It's just like assume every query is a whole query, and this is
Okay.
what you get. Yeah. Okay, so we'll look at the root query. We're going to do it by induction. The worst case is it's a whole query, like this. There's n+1 many children's subtrees. The expectation of this tree is at most the sum of the expectations of the subtrees over n, because remember that the weight of this singleton is 1 over n. So we get there's n+1 of them. Now, since we assumed the depth was small, then these things all have 1. By induction, we get this bound. Yes, should have stated the induction hypothesis. Okay, the inductive hypothesis is that each of these guys have this bound. So a tree of depth inductive hypothesis should be that this is at most product of I equals 1 d of 1 plus over d. If t has depth d. So if my tree is depth d, the expected value e of t is at most this.
N minus I there.
N minus I. Right. Now I'm just going to apply this,
Okay.
and then I get this thing.
Okay.
So
One-
I'm applying this to each ti.
Mm-hmm.
They're of depth d minus 1. I get this bound.
But then it should be 1 plus 1 over n, I think.
I think you have n+1 of them, so that's why, and each one of them, there's a summation missing somewhere, right? The
Yes,
weight
yes,
is 1 over
yes.
n, and there
Thank
are
you,
n plus
yeah.
1 of them,
Yes.
and that's how you get 1
Yeah,
plus
yeah.
1 over n.
Okay.
And then,
Then you bound
using
it by-
standard bound
Mhm.
and the fact that this is the most n over 2. Yes. Should have really gone over these slides, I'm sorry. Yeah, this summation here should be there.
Mhm.
Then I get this bound, and that's the naive bound.
Mhm.
Basically, all I'm saying is that the worst case is when every query in my tree is a whole query.
Mhm.
We're going to use this naive bound plus a little trick in order to get the full bound on the tree. Problem is, well, one problem is that this is large.
Mhm.
This is greater than 1. Another problem is that we don't even have a bound on the depth of the tree. So all bets are off. What we are going to do is we're going to use this little observation that if everything's inconsistent, we can bound the depth of the tree. Together with this naive bound. We're going to kind of put these two things together, and that'll allow us to prove the lower bound. And crucially, it'll come from the fact that it's pairwise witnessing. Okay. So this is the definition of pairwise witnessing. You've seen that. Okay.
Question.
Yep.
Isn't x 2d over n more than 1 for any d?
Yes.
So that one is.
It'll be useful.
Oh.
It'll be useful, but we're gonna do a trick to make it
Oh,
useful.
okay.
Yes. Yes, it's greater than 1, but like, yeah.
So you need
I
to
can
use that.
spoil it by saying this whole, I get this bound for this whole thing here. I get a 1 over n from this. Yeah, I'm going to put that together with that. So I'm going to be able to divide this by n. That'll help. Okay. Yeah, so so the key property is this. So let's suppose we have our tree here that we built. Let's look at some whole query in this tree, H, and let's look at its subchildren, this. Now, I claim that after I make this query, all the one leaves of these trees have to be inconsistent. That means, you know, they all of the paths in here have to map pigeons to two pigeons the same hole or to whole, or sorry, they have to map one pigeon to two different holes. They have to be, they're just not matches. Okay. So how do we see this? So I claim that every path in these trees that ends in a 1 is inconsistent. This is because they come from a pairwise witnessing family. Okay? And L1's like, yeah, the 1-leaf paths. So let's see this. Let's take any 2 1 paths here. And I'm going to, you know, we got to this whole query here by following some path. From the root of the tree. Both of these paths, pi and pi prime, agree on rho. I'm going to let pi and pi hat and pi prime hat be their extensions. So we know that any 2 paths in the same decision tree were inconsistent by definitions of decision tree. You know, send, either map pigeons to, you know, the same pigeon to 2 different holes, or map the same hole to 2 different pigeons. So that means that, because that they're inconsistent, that means that these 2 paths could not have come from the same decision tree. We're assuming that they're, not inconsistent. And if they're not inconsistent, so I want to prove this thing by contradiction. So I'm taking these 2 paths, pi and pi prime. I know that they come from different decision trees because I'm assuming that they're not inconsistent. I'm going to get a contradiction and show that they have to be inconsistent. So if they're not inconsistent, that means that because these things came from pairwise witnessing families, that means that they have to be, these 2 things have to be, the whole paths have to be pairwise witnessing, and they have to be a matching. These little guys have to be a matching. Right, because if they're 1 paths, that means that they agree with conjuncts that are pairwise witnessing, so they themselves have to be pairwise witnessing because they're not inconsistent. And these 2 things have to be a matching because these things were not inconsistent. And then because they're a matching, that means that the whole paths, these whole path things, have to only collide in 1 hole, which contradicts that they're pairwise witnessing.
Can you go over that again? I think I
Yeah,
didn't
yeah.
have it from the beginning.
Yeah.
So you have
So we're supposing that we have these two paths, which
Mhm.
are labeled 1.
Mhm.
So that means that they agree with some pair of conjuncts from pairwise witnessing families.
Mhm.
We assume that they're they are not inconsistent. So that means that they have to come from 2 different decision trees.
Right.
Because if they came from the same decision tree, then they would be inconsistent. So like,
When you say it comes from different decision trees, you mean from the conjuncts? No, sorry, what are
yeah. So inconsistent. So sorry, 2 different decision trees mean like sub-decision trees. These 2 guys.
okay.
So inconsistent again means like it's not a matching.
Okay, so pi and pi prime, if they were in the same decision tree, they would differ in something, and then they would be inconsistent at that point, like when they branched out.
Yeah.
Okay. So pi and pi prime have to come from different decision trees.
Yeah.
Otherwise, they're inconsistent, and then they're labeled. And what happens if they're inconsistent?
So we're assuming they're not inconsistent because we want to prove that they have to be inconsistent.
Okay. So they come from different decision trees. Okay.
But that means that each of these guys are matchings. They agree on this thing. They only form a collision in this particular hole.
Why? When you say pi prime is a matching, it means that the conjunction of them is a matching?
Yes. Yeah.
Okay, because otherwise it's inconsistent.
Yes.
Okay. So the conjunction is a matching, so the only difference in one hole, okay.
Yeah.
But since it's pairwise witnessing, it should find a solution for both the pigeonhole.
Exactly.
Okay.
Yeah. So pairwise witnessing basically means that any one path here, any pair of one paths, if you take the and of them, you squish them together, then they have to find a collision in both the 2 instances. But
but are you not using the uniqueness there?
yes, yeah. So you are using uniqueness.
Okay.
Yes.
Okay.
Yes, good. Yeah. Problems with writing slides when you don't have much sleep. Yes. So this is where you're going to use the uniqueness. Because otherwise you could have 2 different things that are exactly this, witnessing the same.
They're coming
The
from
same
the same conjunct.
Yes.
Yeah, then they don't have to collide in 2 holes.
Yeah. Yeah. So we know they're not inconsistent. That means that they don't query the same pigeons as the holes down here, or are they? Yeah. These guys
They agree on it.
Yeah, or they agree on them. Yeah. If they query a similar, like a same pigeon or same hole, they're going to set them the same way. These guys are matchings, like their and is a matching, and they're not inconsistent. But since the whole thing, these 2 paths had to be pairwise witnessing, that means, and we only saw a solution in one hole, this would be a contradiction, therefore they have to be inconsistent. So what this means is we take a whole query and we